Okay, so we're moving on to finding internal forces in members. What we'll do is just run through how this works and how you find them with the models first, and then we'll look at how you do it on paper. I'm just trying to get this to work first. So this is just to give you a basic concept of what we're doing with the maths here. We'll just do it with the model first. And so what I'm going to try and do here is I'm going to try and put a tension force on this member. So I'm going to stretch it out like so. Hopefully it holds. Not so much. Oh, I got it to work before. Why can't I get it to work now? Okay, so I've stretched out that. I've got another one here. It's the same. The basics of what we're doing, so we've got two forces applied on that. Just assume they're equal. I haven't drawn them very well. Just assume they're equal. The basics of what we're doing is when we're trying to find these internal forces, we're imagining cutting this member like so. That's what we're imagining. Okay, let me tidy that up. We're imagining cutting that member, and then we're thinking, look, what do we have to do to this to get the same situation as before? And so we've got a force there. We split this in half now. What we'd have to do to this to get the same situation as before is we're going to have to get a tension force. We're going to have to pull it. So it's pretty obvious that you're going to need a force on the other side going in the same direction with the same magnitude. Now there's another way to think about this. You can just think of this as a free body. So we've cut it here. You can think of this as a free body. We've got a force on one side. For static equilibrium, we need to apply the same force on the other side. And the same would be true of the other half. Let's see if I can fit all this in. So for that one there, it's got a force here. That's that external force. To find the internal, to reveal the internal forces, don't know if I've got enough arrows actually. To reveal the internal forces, we've cut it in half. And so we would need, I'll just move it down the way so I can fit it all in. And the other half, the external force is there. For static equilibrium, we'd need to add another external force on the other side. And these two forces would be the same. Okay, these two internal forces. We can tell it's tension because, or we can tell it's positive because tension is positive. It's going that way. Okay, just look back at the sign convention. So this would be a positive axial force. So you can just say it's a tension. Negative axial force, it would just be a compression. Okay, so that's a kind of trivial example. And by doing that, we'd get the same thing in these sections. So we'd be pulling them apart like that as we got in the original one. Now, let's try another one. We'll do some relatively simple stuff. So imagine, for the case of bending now, and we'll get cases where we combine everything later. So imagine I'm applying a couple of pure moments, equal and opposite here. Like so, that would tend to bend this like that. So I'm just applying those pure moments with my fingers, tend to bend it like that. So if we took half of this, so again, if we cut this in half, can't remember which way around they went now. Looks about right. So if we cut this in half and we had a moment on this side, so let's just put it off there a little bit, and there was a moment on this side. If we're going to get static equilibrium of that half, we need an equal and opposite moment on the other side. What would that do to this? It would bend it like so. Okay, and we'd have to do the same thing with the other half. We'd have to have equal and opposite, so the external force is like that. To get static equilibrium, we'd have to have the sum of all the moments equals 0. So we would need an equal and opposite moment on the other side. And these are the internal forces. We've revealed them by cutting it in half and then making sure we've got equilibrium on both sides. That's the basics of what we're doing. I guess we could also do it with shear. And so if we had shear blocks like so, we're bending it like this. And so in other ones, well, let's try and get positive. That would be positive. So that's a positive shear like that. Did I just say we're bending it? We're shearing it like that, sorry. And so equal forces, opposite direction, and we're maintaining that direction on these. We're not allowing it to spin around. That would just be a couple. We're maintaining the direction, and that's a shear. And so for that situation, which one do I want to cut up? Cut this one up. So slightly different size. So you just imagine cutting it down the middle. Then we'd have two halves. Could have cut it straighter, I suppose. And so we would have this external force on this side. So we would just think about this one on its own, and we'd try and get static equilibrium. So we'd have to have, let me just think about this for a minute. Yep. So for static equilibrium, we would need to make sure there was an equal and opposite force in the other direction, and that way you'd find static equilibrium for this. We'd actually have to think about moments and stuff for this. This is a bit simplistic, the way we're thinking about this one. But for now, that'll do. We'll get into the details in a minute. And for the other one, you need the same thing. So we'd already have an external force like so. And we'd need an equal and opposite force to ensure that the y components all equal 0. And so therefore, we'd be able to find these two internal forces by cutting this thing down the middle and then finding equilibrium of each half of that object. And that's the basis of what we're going to do now with a bit of maths.